This is a podcast about how two DNA strands bind together with hydrogen bonds. And hopefully the diagram on the screen is something which you are familiar with. We've got three basic diagrams. We've got one, the double helix of the bases facing inwards with the blue sugar phosphate backbone, and we can just see the hydrogen bonds between the bases there. If we go into a little more detail, we should know now that purines bond to pyrimidines, so that's A, T, and G, C, and that A and T have two hydrogen bonds, and G and C have three hydrogen bonds. And so we have, hopefully, that information safe and sound. And then when we look at the third diagram, which is the main one here, we can see that we have phosphate sugar base as a nucleotide, which forms phosphodiester bonds to the next nucleotide to create a polynucleotide. And so we also know that the bases hydrogen bond with each other inside, and that the strands run antiparallel to each other, antiparallel. And that means that this strand here goes from 5' to 3', and this strand here goes the other way, from 5' to 3'. So they're running in opposite directions. And what I want to focus on here is the slightly strange phenomenon there. If I just put this out, where we can see that the deoxyribose sugar on this strand, the left-hand strand, can you see that it's flipped around the other way compared to this one? So this, on the left-hand strand, we have perhaps a more orthodox nucleotide. But this one on the right is upside down. Can you see that its base is orientated in line with the base, but its deoxyribose sugar has its oxygen, which is there, pointing down, and its phosphate below the sugar and base, not above. And that is why they are antiparallel. The right-hand strand is flipped, so it's running in the opposite direction. And so we can actually work out why this happens due to the fact that adenine and thymine and guanine and cytosine have specific atoms within them which lead to hydrogen bonding, which fit together like a jigsaw piece. And it wouldn't work for the two strands of DNA to form like this. That would not work. Okay, this bonding here would be like a jigsaw piece that doesn't fit. Okay, so that will not hydrogen bond to each other, and overall it wouldn't be energetically favourable, because many of these things happen due to them being energetically favourable. And so in fact the only way that these two can bond together is by us having, just finish that base, by us having an arrangement where the base binds, but then we have an upside down sugar and the phosphate coming off. And you can see therefore that in that arrangement this is upright and this has been flipped. And in this arrangement we would get the hydrogen bonds between the bases that fit together a bit like a jigsaw puzzle. So the next question is why? Well, we need to know a little about hydrogen bonds. So let's remind ourselves of water. Now, water is an amazing molecule, and it's amazing because it forms hydrogen bonds, and this has led to many of the features that we see that allow life on this planet. It has a very high specific heat capacity, which means that water is able to exist in the temperatures on the Earth. It's got an unbelievable level of cohesion, which allows plants to have transpiration streams. And in fact, I could bore you senseless with why water is so amazing. But what I want to focus on today and here now is why water-hydrogen bonds. Because hydrogen bonds are formed when you get a separation of charges which then attract each other. So we know from the very earliest science that we ever did that plus will attract minus. If you've got opposites, they attract, a bit like north and south on a magnet attracting each other. And so this is actually the very simple principle by which hydrogen bonding works. And it's due to a very individual feature of oxygen in hydrogen bonding in water. And it's that oxygen is very electronegative. This is an important word. Electronegative. And what this means is that oxygen has a high affinity for electrons. It pulls them very hard towards its very positive nucleus, its electronegative nucleus. And poor hydrogen is not so electronegative. And so what effectively happens is that the electrons that hydrogen and oxygen share are pulled more closely towards oxygen than hydrogen. So if they were dead in the middle, let's put these electrons in. That's not very clear at all. Let's choose a different colour. Let's say that hydrogen has orange electrons and oxygen and hydrogen both share. So let's make oxygen's green. Now that looks pretty even there, in that if we had those electrons in those positions, oxygen and hydrogen would be sharing them pretty equally. But it doesn't actually work like that, because oxygen is so electronegative that it pulls the electrons much closer to itself.